I want to demonstrate the process of doing multiple regression analysis in Excel. Let's say in Excel you've got some data, you've got assay values for both zinc and lead for a bunch of samples, and let's assume that each of these columns is a sample and this paired data is the assay data for each sample. What I'm asking myself at this point is, to what extent does lead grade act as a predictor of zinc grade? And to do this in Excel, it's pretty straightforward. What I want to do is go to Data, Data Analysis, and choose this regression option. Click OK. My input Y range is going to be the value that I want to predict, which is going to be zinc. And the X range is going to be the predictor value, in this case, lead. I want to make sure I've got this labels check marks ticked, and then I'll accept the rest of the default settings. Press OK. This is the output that Excel provides. It's a bit of a difficult table, but really the values that I want are here and here. These values at the bottom will allow me to build a linear equation that attempts to estimate zinc grade based on lead. And then this value up here, the adjusted R squared, this R squared value gives you a sense of what fraction of the variance that you find in the zinc grade can be explained away by the equation that relates lead and zinc. I know that from doing histograms of zinc and lead grade, that these grades this data is highly positively skewed. Here's an example of my zinc histogram. If you don't understand how I created this, I've got a separate video describing how to handle histograms, how to create histograms with positively skewed data, and I'll put a link to that video here. But ultimately, I felt the need to apply a transformation to my data to de-skew it, and I want to apply that transformation to my data as well when I'm doing my regression analysis. So in that case, what I'm going to do here is fill in some transform values, and the transformation I happened to use was the following formula. I took the zinc grade, I raise it to the power of 0.01, and then divide by 0.01. I actually applied that exact same transformation to lead grade as well. So I'll copy that formula over and copy it down for all these samples. So now I've got two new columns of data that I prefer to use in my regression analysis than this highly skewed data. So in this case, I'm going to go data analysis again, rerun my regression, but change my input values. I want this to be the Y range, the zinc, transform zinc values, and then I want my transform lead values to be the X range. Accept the rest of the inputs, and here's my output. Now we can see, again, here are the parameters I need to build my linear equation, and then my R squared is up here. And you'll notice that the R squared now is 50%, whereas before it was only 17. So that's the magic of using transformed data. Using data that's not highly positively skewed helps you see some of the correlation between two parameters much better than if you're working with the raw, highly skewed data. Here's another version of the problem with a little more complexity. You see I've added silver grade in addition to lead and zinc. And then I want to know, to what extent does lead plus silver help me understand or help me predict what the zinc grade is. Silver is also highly positively skewed, so here I've got the transformed values for all three elements. So to include this one, and again, it's pretty straightforward. Run my regression. My Y input range is going to be the transformed zinc values, and the X values are going to be the lead and silver column. And here's the table. Here are the data I need to write my linear equation. You can see now silver is included as one of the parameters. And then again, here's my R square value. And we can see that R squared has improved slightly with the addition of silver. So now lead and silver included is a slightly better predictor of zinc than just lead. Here's a new variation of the problem where we have zinc grade and we want to use lead grade and silver grade to predict zinc with the addition of this other piece of information called alteration. So we have a couple of different alteration types labeled 1, 2, and 3, and we want to know to what extent this type helps predict zinc grade. But the problem here is that these are categories and they're text values and they're not numbers. So what we want to do is, in a sense, transform these categories into binary data. And here I'll show you what I mean. As an example, I'm going to take these values, just paste them over here real quick, temporarily, and I'm going to go to the Data tab and click this Remove Duplicates button. And what that's going to do is reduce this list of values to the 3 unique values that are found in that list. And now what I'm going to do is I'm going to take, of the 3, I'm going to take 2 of them. I'm going to take all of them except for 1 and create new columns dedicated to these 2 alteration types. Then I'm going to write a formula. It's an if statement, which is going to ask if this value here, and I'm going to hit F4 3 times to lock in that column, is the same as this value here in the header line. I'm going to hit F4 twice to lock in that row. Then give it a 1, give this cell a 1, otherwise assign it a 0. So what I'm ultimately doing is, I'll copy this down, is saying, hey, look, for this column, check the value here. If it's the same, give me a 1. If not, give me a 0. And I'll copy that over to alteration type 2 column. And again, I'll ask the question, if this value is the same as this, give me a 1, otherwise give me a 0. Now, I've not included that third alteration type. I have in the past, but that usually leads to this error in the regression analysis when you include all 3 possibilities. Now, all 3 possibilities are covered, like in this situation here, because this sample is neither alteration type 1 or alteration type 2, and that there's only 3 in the list, then you have lost the information that this is alteration type 3. But just by adding that third column, alteration type 3 column here, will generate an error in my regression analysis. So we're leaving it out. So we've taken this categorical data, we've converted into binary data, and now we can use this suite of information to run our regression. So the input range for Y is going to be the transformed zinc values, and the input for X is going to be lead and silver and alteration types 1 and 2. Okay. Okay, so now here we have the output for that latest regression. We've got not only lead and silver, but also these two alteration types included in our linear equation to estimate zinc. And we can see that we've had an improvement again in our R squared to a higher number. So now we're saying 83% of the variance in zinc grade can now be accounted for in in the equation that includes these parameters. Here we have another slightly more complex version of the problem where not only, again, we have lead, we have silver, we have alteration, but we also have added this rock type category. So again, it's categorical, it's text values. We've converted those text values into binary over here. Now I happen to know for a fact that rock type 1 and rock type 2 have no correlation with zinc grade. And I set it up that way purposely, so just to demonstrate what do you do with predictor variables that have no statistical significance. So we're going to run this regression analysis again, including all these candidates for predictor variables, and let it run. And here are the results of that analysis. And what we can see here for rock type 1 and rock type 2, this column here is these values are quite a bit higher than the ones we had over here. And the way to read this value in particular for rock type 2, this p-value is saying to me that there is a 99% chance that the correlation that I'm describing here between rock type 2 and zinc, there's a 99% chance that that's actually just a random occurrence. There's no truth to it. And for me, and I think for everybody, that is that chance is so high that I'm compelled to take rock type 2 and exclude it from my regression analysis. The threshold value I use for this, I want these values to be very low. In fact, I want them to be 0.05 or less. I want the correlations that I'm establishing with this formula to have a 5% chance or less that it's due to just a random occurrence and not that it's not real. Now both of these, rock type 1 and rock type 2, are showing p-values of much more than 0.05, but I don't want to get rid of them both at the same time. I want to get rid of the highest one first, rerun the regression, and then that will ultimately lead to a change in the p-value for rock type 1. And if it's still greater than 0.05, then I'll go and remove it so do this in a stepwise fashion. So let's do that. Rock type 2 we said was probably very unlikely to be a driver, so I'm just going to move it out of the way here. I'm going to rerun this regression with the zinc again, but I'm going to change the input, the predictor variables, to just these 5. So now we see our results table again, and then if we look here at the p-values, we see that the p-value for rock type 1 has decreased. It was in the 30s, 30% before, but it still exceeds our 0.05 threshold. So I want to finish this off, I want to go back to the original data. Like before, we're going to remove rock type 1 from consideration like we did rock type 2. and then rerun the regression. Only using these 4. So here are the results. Down here we have the input for a linear equation that we're going to use to predict zinc grades. And here we have the R-square value, which tells us to what extent this equation can explain away the variance you see in the zinc values. So that's how to do regression analysis with multiple predictor variables that at times need to be de-skewed or need to be converted to from categorical text values to binary.